Welcome in this video where we are going to implement the initial paper that introduced diffusion model. So that was the very first paper on diffusion model, and sometimes it's a bit this paper is a bit overlooked, so I'm really happy and excited to do this video. It was written in 2015 from researchers from Stanford University and UC Berkeley. I don't know if the authors were aware at that time of the impact the paper would have, not just inside the research community, but to everyone basically. Now generative AI is impacting a lot of people, mostly related to image synthesis, but also beyond that. Now we can do much more with generative AI. And diffusion model are a big part of that. So I'm not sure if those authors were aware of that, but yeah, very nice paper. So we're going to reproduce the figure 1 from the paper in this video. To the best of my knowledge, there are no public implementation that are able to get the same that were able to reproduce this figure with high accuracy. And basically these are the results we'll get by the end of this video. So very close to the results from the authors. And I'm not aware of any other implementation that are able to reach that. So yeah, if you're interested into that, stick to the end. I'm also super excited to announce that we've just reached 1,000 subscribers. So thank you very much for that. And I will make a contest at the end of this video with the opportunity to gain, to win some Amazon voucher. So if you're interested into that, also stick to the end. But yeah, let's dive into diffusion models and into the code. So as always, we're going to use PyTorch to implement everything related to machine learning. And then we will use other libraries such as NumPy and scikit-learn to load the data on matplotlib to plot the results. So we can start to load the data and to create a function to sample a batch from the training data. So what we are going to do is to use this make Swissword function from scikit-learn. Basically it will return this Swissword distribution. So we are sampling some data and storing them into X. And then what we do, we only keep 2 columns from X. So because make Swissword, I think it's 3D data, only 2 columns. So the first one and the third one, we select them. Then we scale the data, we divide them by 10 to have something that is to get roughly the same scale as the data from the paper. And then we do some we do an affine transformation. So we flip the y-axis to get exactly the same shape as in the paper. Actually, this is not important, this is not needed, but this is just to make sure that the plot we make here is the same as this one, or roughly the same. Okay, so of course until now nothing related to diffusion model, but yeah, let's move on. So the diffusion model are using neural networks for the reverse process. We'll implement the reverse process in a moment, but therefore we'll need to rely on neural networks. So on those neural networks need to be time dependent. We'll talk about that in a moment. So let's implement neural networks so that we can use them for the backbone of our diffusion model. So we take as input n, this is the number of time steps. So for this type problem, it is the big T that is equal to 40. This is the hyperparameters that were used in the papers. So we use 40 time steps. The data dimension is 2. We have 2D data, and we're using 64 hidden dimensions for the MLP. So because our MLP needs to be time dependent, we need to implement our MLP to be time dependent. So there are different ways to do that. Either we can take the time as input and do a conditioning. So to condition the neural network on the time. This is an approach, for example, that is used in stable diffusion on more recent papers on diffusion model. But in this initial paper, what they did is basically as if you had 40 neural networks. So basically you have 1 neural networks per time step. So 40 different neural networks. So each of them is independent, and therefore it's time dependent. It depends on the time, because for each time steps you have a different neural networks. But if you try to optimize things a bit, instead of having 40 really different neural networks, you can try to share some weights so that you reduce computational requirements. So basically the head of the neural network is shared between all time steps, and then the tail of the neural networks are different for each time steps, and therefore you get a neural network that is time dependent. Depending on the time that you get as input, you will use a different tail, and therefore the neural network will behave differently. Of course, we are not used to those approach. These are there is a specific name for that. I do not recall it. But yeah, basically nowadays we are more used to like just condition the embedding as input to the knowledge work or at further layers. But this is also an approach to do that. And then we can implement the forward function. So we take as input x, and again the knowledge work is time dependent, so we need to take t as input, which is an integer. And then we compute the hidden features from the head of the knowledge work. That will be the same for all time step t. And then we can compute the output of the knowledge work using the tail at the given time step t. And therefore, if you give different values for t for the same input x, you will have different values. Okay, so now that we've implemented the MLP backbone, it's not the most interesting part. We can move on to what is it's most interesting for this video, the diffusion model part. So the diffusion model takes as input an n.module, so a function approximator, a neural network. We've just discussed about that. The number of time steps, again, we'll use 40 in this video, on a device on which the device on which everything will run on. Usually we want this to run on GPU. So we can store the model on the device. Then we can create betas, so the variance scheduler. In this video, I really focus on the implementation. I will not dive into the mathematical details on the equations. If you want to learn more about the equations, I advise you to read the paper and then come back to this video. There are a lot of great tutorials online, or maybe I also have a course about diffusion model, a 10-hour course. That is very, I think it's best rated on Udemy at the moment. So yeah, if you want to learn more, I invite you to have a look at this course. Maybe it can be useful too. But let's go back to the video. So there is beta, it's the variance scheduler. We're using a linear scheduler. So not a linear scheduler because we're using the sigmoid. So basically we are linearly sampling beta between -18 to 10. We want to take n steps values, and then we take the sigmoid of this and we scale it. We do a scaling and then we offset it. Basically, there are a lot of ways to use to create the variance scheduler. I think the most commonly used nowadays it's just a linear scheduler, but this one worked well for this paper with those data. In the paper, actually, beta was learned. They do not fix it. They learn it with gradient descent. But nowadays, at least as of 2023, state-of-the-art diffusion model use a fixed variance scheduler. So let's just use that instead of learning it. So once we've computed beta, the variance, we can compute some variables that are dependent on beta. So we can compute alpha bar, and we can just store the number of time steps, and we can store the variance. So basically it's just the same as beta. Basically beta is the variance, but we just give it a better name so that it's clear. Basically alpha and alpha bar are not needed. We could everything could be expressed as a function of beta, but this is just like a convention or to make the equations or the notation easier to understand. So now that we are done with the constructor, we can implement the forward process. So diffusion models are made of two components, the forward process and then the reverse process. So let's start with the forward process. So basically the forward process starts with the data, and we randomly add a stochastic noise little by little until we destroy the signal. And once the forward process is done, we can compute a reverse process. It's the next function we implement to go back from noise to the data distribution. So for that process, we receive x0, so the data, directly from the training distribution. T, basically it tells us where we need to stop. Either I need to stop at big T over 2, for example, I will get those data. While if I stop later, let's say at T equal big T, I've completely destroyed my signal. So basically, T will give us the amount of noise we need to add. So I try to stick to the equation from the paper to make it like easy to understand. So in the paper, T goes from 1 to 40. And because I want to keep the same convention as the paper, here I'm just doing T minus 1 in the code because we want to start indexing at 0. But when I call this function forward process, if I put t equal to 1, that means I want to do one step of forward process. It does not make sense to say okay, t is equal to 0. If t is equal to 0, it means I'm doing one step of diffusion. So basically, if I call this with t equal to 1, that means I'm doing one step. But because in Python we start indexing at 0, I'm just doing t equal to t minus 1. This is just a convention. That's how I've decided to work. There may be better ways to do that. Once this is done, we can compute xt from x0. So basically in the paper, they explain how you can sample from xt given xt minus 1. So when you know xt minus 1, you can sample xt. So if I know x0, I know x1, I can sample x1. If I know x1, I can sample x2, and so on and so forth. So this one is what is described in this paper. So if I want to sample xt given x0, I need to write a for loop that will iterate. If I want to do a 10 time step, I can do 10 loops and then use this equation recursively to sample x10. The thing is, and it's not mentioned in the paper, but they did it in the code, if you know x0 and you know t, you can directly compute xt without doing a for loop. There is an equation you can use that will give you xt given x0. So using those equations, maybe you can try to do it mathematically. Otherwise, if it's too complicated for you, just have a look at tutorials to see where we get there. It's also explained in my course if you're interested. But we can directly sample from xt when we know x0. So it's a trick. It's explained in other papers, in a follow-up paper. For some reason, the authors already use this trick in the code, but they do not mention it in the paper. So, okay, we sample xt given x0. This is the formula. So you see you are using alpha cumfold, and that's why we computed it in this line 43. We pre-computed this value. Again, it's just a function of beta, the variance. But we use alpha cumfold to make the notation on the code easier. And then once we've computed xt, we need to compute some summary statistics. So let's go in the paper to understand that. So basically, we need to we have a generative model of data. So usually we train them by maximizing the model log likelihood. And after some maths, what we want to minimize, it's really like the KL divergence between this distribution, Q of xt minus 1 given xt on x0, on the posterior distribution x of t minus 1 given xt. So what we've just done is we've sampled xt given xt minus 1 on x0, which is equivalent to xt given xt minus 1. But what we really want is to this distribution. So basically what we're doing in this code is really computing the mean and standard deviation, sigma, of this distribution. Again, just focusing on the implementation, I will not go into the details, but try using all those variables to compute the summary statistics of this distribution. So that means that because this is Gaussian, and this is Gaussian as well, the KL divergence is just a function of the mean and variance of each distribution. So now that I have the mean and standard deviation of this function, of this distribution, in my code I will need to be able to compute the mean and standard deviation of this distribution, and based on those values then I can compute the loss. But we will do that in a moment. So let's move on. But if we summarize what we've just done, we are doing the forward process. So at a given, I'm computing xt at a given time step t. So if I receive x0, some data there, and if I receive some time step t, I will add the noise to run the forward process. And what I'm also doing is then for given time step t, I'm computing the summary statistic of the posterior distribution q of xt minus 1 given xt on x0. So once this is done, we are done with the forward process. If you want to play a bit with the code, just try to run this function with t equal to 1, 20, 40 to see what's happening. And now we can move on to the reverse process. The reverse process takes xt as input on some time step t. Basically, we need to tell to the reverse process what is t, if this means x10, x20, x30. And then from this, it will compute, it will sample from xt minus q of xt minus 1 given xt. So basically it will do one step of, it will invert this process, it will do one step of a reverse process. So removing the noise in some way. So again, we want to start indexing at 0. So we do t equal t minus 1. If t is equal to 0 after reindexing, it means if t is equal to 0, it means we don't need to do any step of reverse process. So we're just returning xt. Again, it's a convention. We could have raised an error. There are a lot of ways to do that. But if t is equal to 0, I'm just returning xt. I'm not doing anything. There is nothing to reverse. And then basically this is where our model become useful. Our model will predict the standard deviation, the summary statistic of this distribution. P of xt minus 1 given xt. The neural network is predicting the summary statistics of this distribution. And basically I will be able to train this model by computing the loss with this distribution. So I have the mean. We are not computing we are not outputting the standard deviation directly, because the standard deviation is constrained. It should be positive. So basically what we do, we compute the log variance. It's usually what we do when we need to predict the standard deviation with a neural network. Instead, what we predict is the log variance. It's much more stable numerically. And then from the log variance, we compute the standard deviation. So first the variance by taking the exponential of it, and then we take the square root to get the standard deviation. And then we can sample from p of xt minus 1 given xt. Basically here, line 71, we're just sampling from the Gaussian distribution. And this is done just by taking the mean and then adding some noise scaled by the standard deviation. So if I sum up what we've done so far, we've implemented the forward process that sample from the forward division process and compute the mean summary statistic of the distribution q of xt minus 1 given xt on x0. And we've also implemented the reverse process that does one step of reverse process and also returns the summary statistics of p of xt minus 1 given xt. And once I've those functions implemented, I'm done with my diffusion model and I can combine everything into the training function. Well, we're not really done. There is still this sample function to use. It will not be used during training, but it's basically what we want to do mostly after training is to be able to sample from the diffusion model. So we need this sample function to sample from the diffusion model. Otherwise, we cannot do a lot with the model. So basically, to sample, we need to start from the noise. So let's say we've used a forward diffusion process that will turn the data into a Gaussian distribution. Then after training, we can sample from this Gaussian distribution and then run the reverse process one step at a time to get back to the data distribution. So basically, yeah, we start by sampling from some noise and then we iterate over the number of time steps and we call the reverse process. So yeah, basically we're just calling the reverse process recursively little by little. And this is not needed, but I've added a variable samples to store the data at each time step. Either you may want just to return the last samples, so for example those data, but I've decided to return the data during the whole reverse process so we can plot them and analyze them. And now we're really done with the diffusion model and we can move on to training. Before training, okay, I've implemented the helper function to plot the results. So the function takes the model as input. So the first thing to do is it's sampling data from the data from the data distribution, and then it's running the forward process for 20 time steps and 40 time steps, and then it will plot the results for each of them. So we iterate over the number over the data. So we have three data, the data at 0 time steps, 20 and 40. We iterate over them and we plot the results for each of them. So we are showing the results as in this plot at 0, 20 and 40 and then I'm making my plot a bit prettier by adding labels on setting the y on x limit. So this was for the forward process. Now we can move on to the reverse process, and therefore we can plot them and make sure that they produce roughly the same data distribution. Here I'm doing the same. I'm iterating over 0, 20, and 40 time steps, and I'm plotting like the so samples. So the model.sample, this is what we've just implemented, will return the data at every time steps, and therefore we need to query the time steps that we're interested in. So first 40 minus 0, it will be 40. So the last values for the samples. So that will be this distribution. And then we'll have 40 minus 20. 40 minus 20. We'll have t equal t minus over 2. So that will be those values. And then t is equal to 0. That will be the noise. And again, just making the plot prettier by adding some labels, and then we can save the results. And now that we're done with plotting, so just a helper function, we can move on to training. Training is very straightforward because now we have all the summary statistics we need, and we can just compute the KL divergence between them. So let's see how to do that. The training function takes as input a model, an optimizer to train the weights of the model. We will train for given number of epochs, and we're using this batch size, which is the one I think they used in the paper. So okay, we iterate over the number of epochs. We're using TQDM to see the progress during training. And we can start from, we sample a batch of data. These will be NumPy arrays. So you are converting them to PyTorch and putting them on the device. Then you are sampling t randomly. So you see that, again, I will not dive into the equations, but here there is a sum over t. But yeah, we can get an unbiased estimator of this loss by using an expectation here instead of the sum. And basically this is what they did in the code of the paper. But again, this is described in a lot of tutorial or in my course on Udemy. So basically what you do, you randomly sample data, you randomly sample t, then you run the forward process, and then you run the reverse process. So you can kind of see that as an auto-encoder. You encode the data, then you decode them, and then you'll compute the loss between the initial data on the reproduced data. But here we're not using a deterministic loss. We're comparing the distance between two distributions, and therefore we're using the KL divergence between the likelihood and the posterior, similar to a variational autoencoder, and therefore we compute the difference between the two mean and the two standard deviation. But basically what we're really doing is computing a difference between two distributions. We want to make the two distributions the same. So we compute the KL divergence. This is just the KL divergence between two Gaussian distributions as a function of the summary statistics, and then we can take the mean of that and then do a gradient descent step. So put back the gradients to 0, compute the gradients using loss.backward, and then doing one step of optimization, so updating the weights using the gradients. And then we are done. We can just put everything together. So we can just define the device, create a model, put it on the device, and then call generate the diffusion model on top of the model backbone. That is just a MLP. We can create the optimizer. We're going to use Adam with default learning rate 1e minus 4. And then we can just call the training function with the model on the optimizer. And finally, we can plot the results with the trained model. So you see that once everything is created, it's very straightforward. And in 5 lines of code, you can train your model. Well, you can train your model and plot the results. So I really hope you like this video. I will have more video coming around diffusion model. For those of you that are interested in NERV, there is also a lot of videos about NERV that are coming. So subscribe for more content about that and also about machine learning. Again, we've just reached 1,000 subscribers, so thank you to everyone that has subscribed. And therefore, I will make a contest where you can win a $50 Amazon voucher. If you're interested, just leave a thumbs up to this video and put a comment about a paper, like a machine learning paper you want me to implement in 100 lines of code. So make sure that it's feasible. Do not give me a paper like a very difficult paper that will take tens of thousands of lines of code. So yeah, just a comment, a thumbs up. In my next video 2 weeks from now, I will choose the winner based on the comment and on the paper suggested. And the winner will win a $50 Amazon voucher. So thank you again, and see you in my next video.